This is digital circuits. Maybe it is. And we're in chapter 5. And we're doing stuff there. Okay, so that's good. So we have things that are ones. We have things that are zeros. We have things that are true. We have things that are false. We have things that are on. We have things that are off. We have things that are 5 volts. We have things that are 0 volts. Basically, that all means the same. 1 true, on, 5 volts, 0 false, off, 0 volts. Those are just euphemisms for the same thought. It's either on or it's off, and that's what makes this a digital circuit class. We have inverters. And they look like that. They have A and an X. They have an algebraic expression. A is equal to, no, X is equal to. X is equal to not A. They have a truth table. AX, 0, 1, 1, 0. So when A is 0, the output's 1. When A is 1, the output's 0. We have ORs. Look like that. We have A, B, and we have an X. And we say A or B in our algebraic expression. We have a truth table, A, B, X, 0, 0, 0, 1, 1, 0, 1, 1. Exhausting all the possibilities. 0, 1, 1, 1, right. And then we have an AND gate. AND gate looks like that. Sometimes it's drawn better than that. Sometimes it's not. A is equal to A and B. That's the way we do that. We have a truth table. A, B, X. 0, 0, 0, 0, 1, 0, 1, 0, 1, 1, 1. That's 0. Yeah. And so both A and B have to be 1 in order for the output to be 1. Then we have the awesome OR gate, NOR gate. Looks like that. A, B, X. X is A or B knotted would be the NOR gate. We have a truth table, ABX, 0, 0, 1, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 0. Okay. And we see that that's exactly the opposite of what happened to the OR. There's the OR. 1, 0, 0 for the NOR. Then we have the NAND gate. We still have 2 more that we haven't talked about, but we'll get to them sometime. So we have a NAND gate, ABX. X is AB knotted. And there's implied parentheses around that. A, B, X, truth table, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0. Both the AND gate, the NOR gate and the NAND gate are universal gates in that they can be used to make any of the other gates. So if all I had, I was on a desert island with a bunch of NANDs or a bunch of NORs, I could do any logic that I could do any place. I can do it all. And so if I want an inverter and I have a NOR, all I do is make both the inputs be the same.
There's a difference between the NAND and the OR, where in the NAND the 0, 0 is a 1, and the OR where the 1, 1 is a 1.
INV, inverter.
I mean, they aren't identical. One's 1, 0, 0, 0, the other's 0, 0, 0, 1.
So in this particular case, if I put in a 0, I get a 1 out. If I put a 1 in, I get a 0 out. The inverter on the NAND side, if I put a if I put a 0 in, I get a 1 out. And if I put a 1 in, I get a 0 out. So what was the complaint that I was hearing?
I thought the NAND
Right here.
and the OR were identical, but the NAND is 0001 and the OR is 1000.
Yeah, the NOR 1000, yeah. And the NAND 1110. Because the AND gate would be a 0001 and everything is inverted in the NAND 1110. So I'm inverting that to give me that. Is that what you're trying to say? Or,
No, I thought the NAND and the OR were similar.
No, they're not that similar. You're trying to tell me I'm teaching you wrong? Yeah, probably so.
No, I thought I had a system
Yeah.
and I don't.
Yeah, you don't. All right, well, that's okay. If I want an OR, then all I'm going to do is take a NOR and put an inverter on it. If I want an OR, I'm going to invert the inputs of a NAND. If I want an AND, I'm going to invert the inputs of a NOR if I want an AND and I have a NAND, then I'm just going to invert the output. So that's how I'm going to make my universal gates. All right. And if I do that every single day until Thanksgiving, maybe we'll have a chance of remembering that, right? Just maybe. Okay, so we're in section 5-1, and we have a thing called combinational logic. Combinational. And that's what this is all about. This is about logic. How we make that digital circuit bend to our will and do what we want. So if I have x is equal to a, b, or c, d, then how am I going to do that? Well, I'm going to go and say there's a, there's b, there's c, there's d, and I'm going to come in through an and I'm going to come in through an and then I'm going to OR those guys, and I'm going to say that's x. So I have some combination of things that are giving me some output. That's what I'm going to do. I can go the other way, but I'm not going to go the other way quite yet. I've got x is equal to a, b naught, c, or d, e, or a naught, b. All right. So I've got an a coming this way. I got a b going this way. It gets knotted. I send it up there. I got a c over here. I send it up there. I AND those guys together. That's this guy. Okay, then I got a d. Send them there. And I've got an e. Send them here. I'm going to AND them together. Yeah, that's that guy. Then I'm going to go and get a not a. And where am I going to put it? I'll put it in the middle. I'm going to put it there. And then I'm going to get a b. I'm going to put it there. I'm going to AND them together. That's that guy. Then I'm going to take all three of these guys and send them through an OR. And now I have x. So now I've gone and taken the mathematical logic that I'm looking at, and I've changed it into TTL logic, transistor logic, so it does what I want it to do. And it's going to do it on the order of 2 or 3 nanoseconds. So on the order of 2 or 3 nanoseconds from the time that A, B, and C change, A, B, C, and E change, then the X will change. Well, that's quick. 10 to the minus 9 seconds. I don't have to be that fast to have a nuclear weapon blow up. I only need to be within microseconds for a nuclear weapon to blow up. So that's a pretty cool thing. So now I said, well, I got a tank of water here. I got a tank of something. Got a tank of paint. And I've got a low-level alarm. And I've got a high-level alarm. High-level alarm, A. And I've got something in there that goes roundy-roundy. I got some motor that goes roundy-roundy. When do I want the motor to go roundy-roundy? Okay, so I don't want the low-level alarm. If I have the low-level alarm, I don't want the pump to go on. I don't want the high-level alarm. So I want to be between low-level and high-level, and I'm going to turn on pump motor. Okay, and then I'm going to say, well, what is that? Well, if I call this guy A and I call this guy B, then if I go A, knotted, B, knotted, together gives me M. So this guy's on, so I'm at 1 here, I'm at 1 there, I'm at 0 here, I'm at 0 there, the motor's off. So that's not what I want. That won't work. But if I go A, B, an AND gate, M, now if I have, if the high level alarm is off, I want the high level alarm to be off. Off. 0. 1. That won't work either. All right, so what's going to work? I want A to be the high level alarm. I don't want it on. I want B to be the high level alarm. The low level alarm, I do want it on. So now when the high level alarm is off, I get a 1. When the low level alarm is on, I don't want that either, do I? I wanted the first one. I want the low level alarm to be off because I'm not there yet. Okay, so I'm off here, I'm off there, they're both off, they both come to 1. That's the guy I wanted. So I can make a set of logic based on what is necessarily, what's going on in the assembly line. Now, if I look at my program logic controllers, I see that program logic controller, I get 16 bits of stuff at the same time, or I get 32 bits of the stuff at the same time. That's a whole lot of A, B's, and C's, and D's. I mean, that gets me almost up to Z there with 32 bits of stuff just on one lousy input card. So I can make a lot of logical stuff work. Then there's the issue of when do the lights go on? When does the low-level light come on? All right. Now, what is the one thing we love? See, ourselves, the Huskers losing on, do we love that? Ohio State being behind at halftime and still winning by lots and lots. Yeah, what is it that we love? All right, so in our business, we love rules. Now, if I gave you all the rules for what we do, and we just follow them, so the sophomore class wired a light to come on, and they wired a switch that was going to turn on the light. Okay, that's fine. And all last semester, what did they do? They wired a switch, and they wired a light. Okay, so I come to the first one. Who was he? I forget who he was. He'll come to me. Anyway, and we push the button, and the light comes on. And we let go of the button, and the light goes off. Is it right or is it wrong? I got my red thing here. It's wrong. Now, wait a minute, that's what it was supposed to do. It was supposed to turn on the light when you push the button. How can it possibly be wrong? What could make it wrong? The light came on. No, you let go of the light, it goes off. Let's go to switch, the light goes off. What was wrong is they had, so you have AC power and you have neutral, and they had AC coming here to the switch going to the PLC, and then they had the PLC going back to neutral, and then they had AC going to a different card of the PLC, that coming back to the light, going back to neutral. Which the wires are perfectly okay, except they have two of them wrong. Which two do they have wrong? Actually, they have all of them wrong, but that's beside the point. We'll concentrate on two. This guy and this guy. What color wire goes back to neutral? White. They didn't run white to neutral. Hey guys, the electric code says white goes to neutral. I don't want to see something. I can't even look at it. White's not going back to neutral. How can I look at it to see if it works if you don't have white going back to neutral? I mean, this is garbage. Now, they knew that. They just spent last semester doing it right after I cut their wires. But they knew that. And they still sat there and wired them up because it was more convenient to use that wire. But I don't care if it's more convenient. How about these blue wires? Can I use blue wires from AC?
Red.
Yeah, they should be red. They should be black. What is blue? B-L-A-C-K. Blue is DC. So if I'm going to use a blue wire, it's a DC wire. These are just rules. Rules. Okay, now we're in digital circuit. Why do we have? Why did they do that? Because they forgot everything they learned last semester. Just like you will. Don't worry about it.
No, I'm saying, why are the wires like this for? Or why does it make a difference?
It makes a difference because when I look at it, or your supervisor looks at it, what is he going to want to see?
No,
So-
electrically, why is it making a difference?
So I got this wire. What is he going to want to see? He's going to want to see a wire hooked up here and a wire hooked up there. What else is he going to want to see?
I want to make sure that's a ground.
He's going to want to see a label on the wire here and a label on the wire there, and they better be the same label. And you better not have used a ½ inch too much wire either. Otherwise, you've used too much wire, and wire's expensive. So you better run the wire the right way. Yeah, rules, you know. We don't do that. We use hunks of wire that are already available, and But it's my job to be the pain in the rear end that requires the right color to be used. Anyway, that'll come. Anyway, we got rules. So this is Boolean Algebra.
So, are them colors, so that's just universal through the whole, everywhere you are going the same color?
Oh yeah,
Okay, that's.
there's a book, what's it called? NT something F. And it's the electrical code, and I think it's 79 because that's the last time it was revised. And it's only like 50, 60 pages long. It's not very long. But there's things that are standard that you have to do, and if you don't do it. Now, we're electronic technicians, we're not electricians. So if we're electricians, we'd spend more time doing it. As electronic technicians, we just do it right when we do things.
Does it have to do with like the volts coming out, or the power? Or?
It could, but in this case it doesn't because it's three-phase, 220 volts. So in general, that's not the case. So the size of the wire will depend on how many amps you can send down the wire.
The size of
So,
the color?
yeah,
Color stays on the size?
But no, the color is the color. So a black wire might be an 18 gauge wire, it might be a 16 gauge wire, it might be a 12 gauge or a 10 gauge wire. They're all black. And then perfectly okay to run that from your load to wherever the power is. But when you're going from the load back to common, you're using a white wire. In the house today, go down to the fuse box, open it up, see what you see. You're going to see your fuses, your circuit breakers. You're going to see a bunch of black wires hooked up to those circuit breakers. And you're going to see a bus bar over here that has all a bunch of white wires going to it. And you're going to see another bus bar someplace with a bunch of green wires hooking to it. So you have white for common, and then you have green wires going to ground. You better not be using one of those green wires to go from power to some load someplace. You better not be doing that, because somebody else is going to look in there and say, oh, that's ground. I'm safe being around it. No. All right, but yeah, go open your circuit breaker. Take the 4 screws off the box. Open it up. You're not going to hurt anything. Don't put your hands up where the power comes in because you'll feel the electricity flowing through you. You don't have to touch it to feel it going through you. You know, within 2 or 3 inches, you're going to feel the 220 volts. That's not a problem. That'll teach you to get your hand away.
This is horrible advice, what you're telling me to do.
But look at that. You know, I get inside that panel all the time and do stuff in
Reasons
there.
why you should have a certified electrician skills.
That's right. That's right. That's why the electrician will do it right. Okay, back to rules. So we have rules. All right, first rule. If I have A or B, then that's going to be the same as B or A. Gee, didn't we always know? Since 4th grade, 5th grade, right? Associative rule of addition. 2 plus 4 is equal 4 plus 2. Or is that's not associative, that's associative, whatever it is. No, that's commutative law of addition. Another rule, A and B and C, that's the same as C and B and A. They're the same. Saying that's commutative law of multiplication is what we called it in 9th grade. Now we're calling it Rule 2. Associative rule. A or B or C is the same as A or B or C. A, B, C is the same as A and B and I'll go the other way, C. Too many parentheses. All right, so that's another rule. Distributive rule. You know, if I had 2x times 3 plus y, then that'd be the same as 6x plus 2xy, right? I could do that. But in Boolean algebra, I've got A and B or C is going to be the same as AB or AC. So I'm doing the same thing. I could have A or B and D or what happened to C? C. And I could have AD or AC or BD or BC. The difference between our math and Boolean algebra is in Boolean algebra we're only allowed to be true or false. We're only allowed to be 1 or 0. So that's where the difference is. Okay, another rule. If I have a and 0, I'm going to get false. If I have a or 0, I'm going to be a. If I have a and 1, I'm going to have 1. If I have a or 1, no, I'm going to have 1. Oh, I'm going to have a. All right, you're right. If I have a or 1, I'm going to have 1. All right, turn the page. I'm on 164 now, if anybody cares. If I have a and a naught, I get 0. If I have a or a naught, I get 1. How can that be? So a and a naught. Truth table. A naught, x. 0, 1, 1, 0, 0, 0. A and a naught has to be false, because one of those two, either a or a naught, is false. Whichever one is true, the other one's false. It doesn't matter which one it is, you end up with a 0. A naught, 0, 1, 1, 0. A and a naught, 1, 1. If I have an a or an a naught, or it could be a b or a b naught, or a c or a c naught, either way, I'm going to end up with 1. If I have a double naught, I'm going to have an a. So I got a naught, I'm going to naught it, a naught naught, a. This is the weird one, and the one I always forget. If I have a or a naught b, I'm going to have ab, a or b. If I have a naught or ab, then I'm going to have a naught or b. And that's going to be, I don't remember that one like I remember the other guys, because this is slightly less intuitive. But if I do a truth table and I have a, and I have a naught, and I have b. Okay, so we look at that, guys. 0, 1, 0, 1, 0, 1. So those are my only possibilities, right? And then I look at a naught b. I look at a naught b, a naught b, 0, a naught b, 0. And then I look at a
If that's correct,
or
then that
a
top
naught
should be 0
b.
instead of a plus b. It should be a, actually. A naught b, you have as a 0.
I'm sure it'll work out. All right. I've got 0, 1, 1, 0, 1, 0. All right, so a naught b is a 1, and a naught b is a 0. Okay, and so I look at a or a naught b. A is 0, a naught b is 0, 0. A is a 1, that's a 1. A naught b is a 1, that's a 1. A naught is a 0, that's a 0. So I find that I'm true here, what is true about those guys. So I look about these guys here, and I see that the truth is here and there. Not there, there. Get rid of that guy. There and there. A or B. A or B. Okay, good enough?
Well, then you have A on the very last one, A
Yeah.
plus A not B.
Yeah,
That's 1 plus 0. 1 plus 0 equals 1.
and that's the same thing.
Well, you have 0 for A plus A not B.
But I don't have an A not B anywhere.
A not B is 0. You
I
have
don't
the same line.
I don't have an A or B. So we need an A or B line is what you're telling me. Okay, so I got an A or B line. Where is A or B true? There it's true. 1, 0, 1, 1. Which makes that guy a 1. That's what you're trying to tell me.
That's what I was saying.
Okay, yeah. All right. So anyway, that's just one of those weird rules that you do. On page 166, all our 10 rules, our 3 laws and our 10 rules are all put together in a nice, concise form. And now we have to use them to simplify Boolean logic. Okay, now that's what we're going to do. So we'll look at the problem set on some page. I'm getting there. 218, starting at 218. All right, now, show of hands, in all of your educational experience, how many of you, by the end of a semester in high school, ever got to page 218 of the book?
You got it open.
But yet, here we are, what are we, week 3? And we're on page 218 of the book. Consider that for a moment, yeah, I consider that all the time, you know. So you could, in 9th grade, you had a math book, right? You made it up to page 92, you know, at the end of by Christmas time. Anyway, so we're not moving all that fast, are we? All right, so we're going to look at, I'm looking at 5-7, not as homework, because I'm not looking at the homework, I'm just need a problem to do. And I have something, I got A, B, C, and I do something like that with it. And I do something like this with it. And I do something like that with it. Okay, so I've got A or B. I got B, C. And I got A or B. B, C is equal to W. And I want to simplify this. Okay, so I'm going to go and say A, B, C, or B, B, C is W. Now, when I've done that, all I've done, I've distributed it. That's right. Okay, so that's what I've done. And then I'm going to rewrite it. A, B, C, or B, B is just, I can rewrite it that as B, C. And I'm sure one of our rules that we skipped is A is A, right? Is that one of the rules? Yeah, number 5 rule, A is A. So I look at that and I say, well, I can write this as A. No, I can't. I can undistribute, and I can say A or 1 BC is W, and then I can say, well, A or 1 is 1. So this is just as B, C is W. So now I reduce this.
How did you get the leap from BBC equals BC? Why isn't it B squared C?
because I only have ones and zeros. What is the meaning of b
Oh,
squared?
1 squared is 1, okay.
Yeah.
0, okay.
So I only have, this is Boolean algebra, I'm only true and false. So rule 5 says A and A is A. Okay, there's no A squared, there's no square root of A. So this is B, C, W. I've reduced it to that equation. All right, and then I'm going to say, yeah, sure. All right, so let's see if we can show that in any way. So I'm going to make a truth table. A, B, C. 0, 0, 0. 0, 1, 0. Oh, that's stupid. Can't even count. 0, 0, 1. 0, 1, 0. 0, 1, 1. 1, 0, 0. 1, 0, 1. 1, 1, 0. 1, 1, 1. So those are all my possibilities. I'm going to look at A or B. Okay, so A or B, 0, 0, 1, 1, 1, 1, 1, 1. A or B, right? And then I'm going to look at B, C. B, C. 0, 0, 0, 1. 0, 0, 0, 1. Okay, and then I'm going to look at A or B, B, C. A or B, B, C. All right, so I got 0, 0, 0, 1, 0, 0, 0, 1. Okay, and then I'm going to tell you that that's the same as BC. And sure enough, it is. It's the same as BC, 0, 0, 0, 1, 0, 0, 0, 1. So my Boolean reduction saying that W is BC was in fact correct.
The only thing I'm not seeing is where's that A plus 1 come from? Where's that?
I don't understand something you said.
This A plus 1?
Yeah.
Well, if I go back the other way, A, BC is that guy.
Yeah.
1, BC is this guy.
Oh, okay, got it.
Yeah, so if I go backwards, you can see how I can undistribute to get there. Okay, or distribute. I distributed to get here, but I undistributed to get there. So I'm always looking at things that are something n or 1 or something n 0, so I can get rid of it. All right, we're going to do the D guy next, just to say we did. So 5, 7, D. I have A, B, C. No, we're not doing homework yet. I'm just, if this happens to be homework, that's good, because you're going to want to see it again anyway.
Yes.
And so I got 2 of those guys, and then I've got 1, 2, 3 of these guys going in an OR. Okay, so I got A, B, I've got B, C, I've got A, B, or B, or B, C is Z. All right. Yeah. A, B, or B, or B, C. All right, so I look at the first 2 guys and I said, A or 1, B, or B, C. A or 1 is 1, so this is B or BC. I go B, 1 or C. Well, 1 or C is 1, so that's just B. For a mere $2,000, I put a security system on the house in Georgia. They woke me up at 2 o'clock this morning to tell me it was alarming. Any rain at all turns it on. We put alarms on every single damn window, and all they have to do is vibrate a little bit. So now a window's alarming. That's so small, no one could crawl in anyway. And it won't be until, we're not going to get there until Christmas time. Yeah.
I get a question.
What's your question?
Let's just say C is open on true.
Okay, so C is a 0 or C is a 1?
C's a 1.
Okay, so C is a 1, if that's the case, yeah.
Now you look at your fourth row, and you get B times the quantity 1 plus C. Well, B times 2?
It's only true or false. 1 or 1 is a 1. 1 or 1 is 1. True
Okay.
or
yeah,
true
okay. It's either
is
on-
true.
okay,
It's either on or off. There's no other way.
okay.
Sorry about that. But there's no other way. Yeah. I think that's rule, no, that's not a rule.
It
But
should be.
it should be a rule, yeah. Well, it is a rule. That's the rule 5. Rule 5 says A or 1 is 1. Well, A could be a 1 or A could be a 0. So A could be a 1, so that'd be that one there. Yeah.
Okay.
So rule number 5 does cover the 1 or 1 is 1. Yeah. So that we don't square anything and we don't have any 2's. It's only true or false. Okay. So we're going to look at
So I'd like to disappear from the equation then, if it's like C plus 1 or C1.
well,
Well, no, A plus 1, C plus 1. That's not gonna
if
work.
if it's 1 plus C, then it becomes a 1. So it's a B and 1.
So 1 plus C is a 4.
But a B and 1 is a B by rule 2.
So B is
Yeah.
so then it doesn't need to be shown.
So it doesn't have to, 1 doesn't need to be shown anymore, and that becomes Z. Now, from another point of view, I've got this B guy sitting here. And this B guy is sitting on this OR gate. If this B guy is a 0, it's AND with the A and B. A and C, right? So these guys are going to be 0 too, and everybody's going to be 0. If the B guy is a 1, I'm going to have a 1 there and a 1 on the output. It doesn't matter what A and C are.
Yep.
Okay, so from that point of view, I don't have to do a truth table. I just have to say that's the way it is. Okay, we're going to do
So that's an OR gate.
5, 9, 5, 9, E. We're going to do 5, 9, E. Okay, so Z is A, B, C, or C, D, or C, D, E. Okay, so that's the problem. And what are we supposed to do? We are supposed to draw the logic circuit, simplify the circuit, draw the simplified circuit. Oh, what a pain. Okay, so that's what we're going to do. A, B, C, D, E. Okay. A, B, C, and C, D, and C, D, E, and.
And those all go into an OR.
Or C. All right, so we drew the circuit. Now we have to simplify the circuit. Okay, so I got A, B, C, or C, D, or C, D, E. And I say, well, that's the same as A, B, C, or C, D, 1, or E. Okay. 1 or E is just a 1. So this is A, B, C, or C, D. At that point, there's nothing I can do about it. So I will go and redraw the circuit. A, B, C, D, and, or, and, or. Output Z. So my revised circuit, A, B, C, or C, D. if I had these things hooked together.
Any multiplications and plus additions.
What happened to E?
E went away. I don't need it. See, if E is 1, it's irrelevant because C and D both have to be 1 in order for this to be 1, in which case this guy's 1 already. Okay? If E is 0, then this guy's turned off, and it's irrelevant because C and D can turn on that guy, which turns on this guy. So
How are you knowing when to use the +1 to get rid of the letter?
I have so few things that I can do. I mean, pathetically little tools. I mean, I really don't have a whole lot, right? So yeah, whenever I see it, it's the only one I've ever used, right? I mean, other than I've used the B as B, but in general, I've always got it down to, in order to reduce it, I get it down to a 1 plus E.
But how do you know to do that? Is it just because there's only one E?
No, because I see 2 CDs.
Oh, okay.
Yeah,
So because there's already a CD in there.
That's right.
there's a CD out.
so I have 2 CDs in the same spot. Yeah,
Okay. So it kind of cancels anyway.
yeah, exactly. Yeah. So, would you rather have a different answer, like 20 years experience working the problem set? With that, okay, yeah, 20 years from now you'll be able to do it. Won't be a problem. Just take my job when I retire and teach this for 20 years, and you'll be able to do it too. It won't be a problem at all at that point.
Yeah, the fourth rule says 1 plus E is 1, and then
Yeah.
the second rule says that CD times, or CD and 1 is just CD.
Yeah.
So you just get CD back.
Yeah.
So you chose E because that's the only other one, other than A, B, and C that has a source.
Well, let's look at the. Let's see if I can move this to the bottom for a moment. Oh, that's dumb. Where is it? Copy. Where's copy? I found it. I found copy. Okay, so I got back here to the bottom. All right, so I'm looking at this equation. Can I pull an A out of everything?
No.
Can I pull an AB out of anything? Can I be? How about a BC? Can I do a BC? How about an AC?
Oh, there you go. Okay.
So my vision has just eliminated my ability to do anything with this guy at all. So now I'm looking at this guy and I say, oh, I got a CD in 2 places, CD, 1 or E. Now I can do something. I look at this guy, I can't do anything with him. There's nothing I can do with him. He's sitting out there, fat, dumb, and happy, going to stay forever. So I see it as CD1, and then I see it just CD, and then I ask myself, A, B, C, or CD, what can I do? Well, I can pull out the C, right? I can pull out the C, A, B, or D, but has that helped me any? No, I just made it worse, right? So yeah, I'm limited in the things that I'm going to be allowed to do. And with a little bit of luck, there are tools that we're going to come across sometime in the future, this week.
Now I understand that.
That'll,
Makes
yeah.
perfect
My
sense.
calculator.
That may, oh, something's wrong. Oh, yes, okay, we'll do that next. So I'm going to come up on multisim. As multisim. And in fact, during the test, the computer lab should be available. We should be able to run it and use multisim if we want to, right? And no, but I didn't make my video big enough to use multisim, so I'm totally hosed. Oh well.
You can't pause it and expand it.
Hmm?
You can't pause it and expand it.
Over here on the side
Is the test going to be on schedule?
is of course. What happened? Get out of there. Logic converter. Okay, so there's the logic converter. All right. So I got A, B, that's not a B, A, B, C, or C, D, or C, D, E. That's not an E either. All right. So now I've got, that's not a D. All right, so now I've got the right code in. I go and I take my Boolean algebra and I send it to a truth table. I then take my truth table and I simplify it. Boom. A, B, C, or C, D. Isn't that disgusting? That is just so disgusting. Yeah, an order of 1 to 10. That's pretty disgusting.
And simp is just simplify, you're eliminating what you can.
Yeah. So I'm going to do it again, and I'm going to go back to example 5.8 on page 169. Okay, so I'm on page 169, and I'm looking at this guy, and I've got a parentheses, and I got an A or B, close parentheses. I got a B naught. Notice I'm using the apostrophe to be the naught because I can't put a bar in this thing easily. Or B naught or B C. So did I put in the right thing? A or B, B naught, B naught. Okay, so I did that. I'm going to take my Boolean and send it to the truth table. There's my truth table. And then I'm going to simplify it. And it says the right answer is B naught or C. I look at the bottom of the page, and after I do the Boolean algebra, what do I got? B naught or C. Okay, good enough? And then if I wanted to, I could go and turn it into gates, or I could turn it into gates with nands. I could do that too. So I can do both of those things if I wanted to. I don't want to though. Okay. Okay, we're moving on to 5-5. 5-5. And now the French have to get involved. Anybody like the French? Any Frenchmen in here? Yeah, all right. It's un-American. It's French. De Morgan. Does that sound like French to you? What who was let's see, King Arthur had a wizard. What was his name? Merlin, right? Well, who was Merlin's arch enemy? Merlin. Yeah. King Arthur had a wizard. Yeah. Who was? Yeah. Well, no, the wizard's main engine was Moranga, not Moranga. Anyway, it was another form of the word Morgan, which is really an evil word, Morgan. You know, we don't think about it in our society, but anyway, so this Frenchman came up with this thing that if I have A, B knotted, that's going to be the same as A naught or B naught. And if I have A or B knotted, that's the same as A naught, B naught. And you say, come on, guy. The problem is that during a period of time, no TV, no internet, no radio. The only thing you go is go listen to the opera that they only sang once a month because that's how long it took them to get ready. You didn't. You had plenty of time to think about things that were logical, right? And so Boolean died in 1820, and De Morgan happened sometime in 1830, 1840, and then digital circuits didn't happen, for a long time thereafter. This stuff all could have died if it wasn't for digital circuits. All right, so if I've got an A and a B, so I got those things. I could have a 0, 1, 1, 0, 0, 1, 1. What am I doing? Anybody want to write up on the board here? 0, 0, 0, 1, 1, 0, 1, 1. All right, so if I have A, B, then I would have 0, 0, 0, 1, right? And if I had A, B knotted, I'd have 1, 1, 1, 0, right? And then if I had A naught, I would have 1, 1, 0, 0. And if I had B naught, I would have 1, 0, 1, 0. And if I had A naught or B naught,
1, 1, 1, 0.
I'd have 1, 1, 1, 0, which is the same as AB knotted. Okay, so from the truth table, it's easy to see that we got there. It's not so easy to see looking at it directly. We'll do it one more time.
It's just,
Well, you just believe me that it,
math gets in the way.
Yeah,
Multiplication and addition just kind of screws you up.
yeah. Well, it's not addition, it's ORs.
Or,
Yeah,
yes.
and it's not multiplication. I'm doing ands. All right, but now when we come back to the idea of that guy, so I got A, B. I got A, B knotted, which is the same as A naught or B naught. Okay. So if I go and had A and I knot it, and B and I knot it, and I go through there, okay, I'm going to have A naught, B naught, knotted. I'm going to have A double knot or B double knot. I've got A or B, and that's how we get the universal gate.
The inverse is
Yeah. So now we invert the inputs to a NAND, and we get an OR. And the same thing if I go the other way. If I invert the inputs to a NOR, what's going to happen? I got A, I got B, I got A naught, I got B naught, I got A naught or B naught knotted, I got A naught naught, B naught naught, AB, which is an AND. So if I input, if I knot the inputs of a NOR, I got an AND. If I knot the inputs of a NAND, I have an OR. And that's how we got with the universal gate stuff. All right, back to the homework set. Okay, we did that. Okay, we're going to look at 517 A. Why not? 517 A. We have W, A, B knotted, A or B, A or C knotted. Draw the circuit, apply to Morgan's theorem, in Boolean Algebra, reduce it as much as you can, draw the simplified circuit. All right, so I've got A, B, C. I'm going to come in like this, naught, and then I'm going to take my A and my C. I'm going to knot it, and then I'm going to send it into an OR and call that W. Okay, so I've done the first part. I drew the circuit as originally given me to do. And now I got to use Boolean reduction to get it simplified if possible. Okay, so this is A naught or B naught or A naught C naught. All right, and then I say, well, look at that guy and this guy here. That's kind of cool. I got A naught 1 or C naught or B naught. I got A naught or B naught. Okay, so now I'm going to draw the simplified circuit. A, B, knotted, knotted, forward. What is it, W? W. Okay, we'll go back to,
Let's look at that both of them together.
I don't know if I can do that. Yeah. So we go back to multisim, and we can remember what it is because it's right there. So parentheses, A, B, close parentheses, knotted, or parentheses, A or C, parentheses, knotted. Okay, do I got it right? Yes, I do. I'm going to use the Boolean to come up with a truth table. It already did. I'm going to have it simplify it, and I have A naught or B naught, which you can almost see. Well, I guess you can see it, even from the back of the room, which is, of course, what I had before anyway. Okay, now we're going to look at the last guy, 517 delta for a moment. I have Z, A, B, or A, C, knotted.
The second A is not.
Oh yeah, there is. Not at my angle though, but at your angle there probably is. Okay, so I got that. So we got to draw the circuit. A, B, C, A, B, and A naught or C going through a NOR. C. All right, well that seems reasonable. Now we're going to do some Boolean reduction. A, B, or A naught or C, the whole thing knotted. I got A, B naught, A naught or C, knotted. I've got A naught or B naught and a double naught C naught. I've got A naught or B naught, A C naught. Got A naught, A C naught, or A B naught, C naught. This is 0. A naught A is going to be 0, or A B naught, C naught. So my final answer, A B naught, C naught. A, B, C, knotted, not knotted. Next one, B is knotted, C is knotted, and they're and together. W. Right? I'm going to go back in the multisim. Okay, so I'm back in the multisim. I have to use parentheses. Parentheses, A, B, or parentheses, A naught or C, close parentheses, knotted. So there's implied parentheses on that bar that I have to put in multisim in order for it to do what I want it to do. Okay, Boolean Algebra, I get the truth table, there's a truth table, and right here I got A, B naught, C naught. That's going to be my answer because that's the only guy that has a 1. Truth table, simplify. Boom, A, B naught, C naught. Okay, we'll do problem number 20. All right, number 20. 5-20A. Okay, so I got it. Well, okay, I got to do it. A, B, C, D. A is knotted. B is knotted. Going in through A. Doesn't look like that. An OR. All right, that's good. Coming out. B is okay. C is okay. Knotted. Coming out. D and that guy. Coming out. This guy coming up to there. A NOR. Coming out of there. Everybody coming into an OR. X. Okay. So right here I have A naught or B naught. Here I've got A, B. I got B, C knotted. Okay, right here I've got B, C knotted D. Here I got A or A naught, B naught, or B, C knotted, knotted. So X is going to be A naught, D naught, B, C knotted, the whole thing knotted, or B, C knotted, D. Okay, what was the question? No, everything's fine. So, but if I don't write it down and go through each of those wires to figure out what each of those points are, I can't go and write down X directly. It's not going to work. All right, now Boolean reduction. All right, well, I'm going to have A double naught, B double naught, B, C double naught, or B or C, D.
Isn't that B plus C double knot?
No, it's not. I could have written it B or C knotted like that, and that would have been B double naught, C double naught, which would be BC. But BC double naught is still BC. So this is going to be A, B, BC, or B naught D, or C naught D. And then I can say, well, the two B's are the same. So A, B, C, or B naught D, or C naught D. And I don't think I can do anything about that. Now, there really isn't anything I can do about that. And then I'd write that over again the way it is. Now, the real issue is, can I remember this long enough to get it in multisim? That's the issue. And so can we move this in ways that I can see my equation and put it in at the same time? Yes, there is. Okay, so I can go put a parentheses, A naught or B naught or parentheses BC close parentheses not close parentheses not, or parentheses BC, oh dum-dum, parentheses, you guys did see what I did wrong there, right? Not, parentheses not, D. Do I have that right? I think I do. Okay, so we're going to go from the Boolean to the truth table. I'm going to simplify the Boolean and I've got an ABC, I got a BC naught, and I got a C naught D. So I got the same answer I did. It simplified it the same way I did it. Okay. We'll do, What do you want me to do? ABC right there. B naught D right there. C naught D right there. Yeah, B and B is B. Yeah, no B squared. No 2B or not 2B. Because there are no questions. It's either true or false. There's no other way. All right. Another time.
I drank too much of De Morgan.
5-20. I tell you, these French guys, it gets worse. These French guys did some things that are totally, completely unbelievable.
You only get to drown once,
And
you
then-
can't drown a second time.
Yeah. And then, not only, and this is in the 1800s, not only did they do really unbelievable things, but then those things that they did ended up applying to quantum mechanics differential equation problems 100 years later.
How smart these
You had to use their techniques to solve these equations, and no one even knew those equations existed when they came up with those techniques. I mean, totally amazing. All right, we're gonna look at the B guy now. Okay, so I got A, B, C. I got a naught guy. I got a naught guy. I got a naught guy. Now this is going to work a whole lot better on a bigger piece of paper. I just know it is. So I got a nan sitting there. Coming from here. And coming from there. And coming from here, I got another 3 input guy. 1, 2, 3 is coming from C. Okay, and then I've got this OR gate sitting down here. 2 inputs, one from there, the other one from there. And then these two guys go into a NAND, and then everything's going to come over here into a OR. Why? Okay, so I got an A naught there. I've got an A naught B naughted there. I've got an A naught B C sitting there. I've got a B naught or C naught sitting there. Okay. Out of this guy, I've got an A naught B C B naught or C naught naughted. Okay, so my Y looks like A naught B naughted or A naught B C B naught or C naught naughted. Yes.
So when you do those circles, that means not.
Yes. Yeah, those little circles there means I'm knotting whatever it is that's going in.
That actually makes sense.
Yeah. No, something's wrong. Something's wrong on the other side of the room. All right, so I've got A double naught or B naught. I've got A naught B C or B naught or C naught knotted. Okay, I can do that. No, I can't do that. Why don't I do this? A naught naught or B naught or C naught or that guy naughted. That looks good. Okay, so I got an A or B naught or A or B naught or C naught or B double naught, C double naught. Okay, I only need one A and I only need one B naught. So A or B naught or C naught or B C. Okay, now I remember that we have this funky rule that we can never remember, right? So we go back to our funky rule page. Where's our funky rule page? 166. All right, so if I take the B rule and pick these guys, I'm going to end up with A or B naught or what? Or C naught or B. Okay, now I got A or B or B naught or C naught. What do I have? That's right, 1. Because B or B naught is 1. And 1 or anything else is still 1. So
Did you eliminate that last letter from the previous screen?
It's like 10A.
in 10b, we have a rule that I told you I don't remember. It says if I have A naught or AB, then that's the same as having A naught or B.
Okay.
So I have A naught or AB. So I'm going to have A naught, which is the C naught, or the B guy, which is the extra guy. Yeah.
Okay, that's,
But if I'm not on page 166 looking at that rule, it's going to be hard to apply it to what I do. I'm not going to remember it. After 20 years, I don't remember it. I only remember that I have to go back and find it. Okay? So I ended up with something C naught or BC, and my mind says, there's a rule that covers that. I don't know what it is. I go back and look at the rule. There it is. Okay, now I can use it. So is this really 1?
God, dang, those guys are thinking smart.
What were they trying to
So-
figure out? None of this was allowed. What were they trying to figure out?
Yeah. Well, we'll get to that in another chapter because
They were
we,
using the word.
yeah. Well, you mean the 19th century mathematicians?
Uh-huh.
Well, they were worried about important things like the existence of God and proving the existence of God and proving that there's order to the universe. No, that went away a long time ago. The ancient Greeks gave us the idea of logic being either true or false. So from the ancient Greeks, they had a logic system that we build upon that got us to this point. But yeah, they were concerned about important things like, when is the second coming happening and calculating it and things like that. But they're also interested in working problems that, so if I'm a mathematician, what problem do I want to work? Do I want to work a problem everybody else has done? Or do I want to work a problem that no one else has come up with a unique solution for?
You have to find an application for it. I mean,
That's right.
you have a reason to do it.
There's no application for it. That's one way to think about it. But they were thinking more purely than we do today. We need a reason to do something. The aristocratic class in Europe at the time didn't work. If you sat in the pub and you talked to somebody about something, you couldn't talk about fantasy football, right? And you couldn't talk about Ohio State winning last night. You couldn't talk about any of those things. You had to talk about something. And if you didn't have some uniqueness to your discussion, then why should I bother listening to you? I'll go listen to somebody else.
Yeah.
And so, you have to have plenty of pork. You have to have cigars. You know, you may have to have some cocaine, I don't know, but,
This is for electricity.
so now the,
For electricity, let's figure this shit out.
yeah, that's right. There's no computers. You can't put it on multisim and see if it's right.
I mean, you're
Yeah.
trying to teach me what he thought so many friggin' years ago, and I can't even catch what he
Yeah.
made
So,
up.
yeah, so 200 years ago, yeah, you did this. Okay, now we're gonna put this in multisim and see if it agrees. A naught B naughted, or parentheses A naught B C B naught
Or C naught.
or C naught, close parentheses, naughted. Okay, so that's what I think it is. And we're going to take it and make it a truth table and say it's all ones on the truth table. So when I simplify that, it's just going to come up with nothing's going to be there because there's no A, B, or C that can be shown up. The answer is 1. That's why it's all ones up there. Yeah. So that's all there is. All right, one more topic. And now we've been cussing out the French, right? So now we're going to cuss out the Russians. Okay, so the Russians are next, and Kirchhoff. And you think of Kirchhoff and you think of the guy on Star Trek, right? Yeah. I mean, isn't that Kirchhoff? Yeah. So, and you're going to get in circuit analysis, there's Kirchhoff stuff too, right? Yeah. So this isn't Kirchhoff. This is Karnaugh mapping. Karnaugh mapping. All right. So what we're going to do is we're going to say we have something that's AB and we have something that's CD. And we're going to make some lines. Now the first time I saw this, we were using a 7x7 one. So you guys are pretty blessed in that you only are going to look at a 4x4 one. All right. And we're going to go A naught, B naught. Now what's A naught, B naught? That's basically 0, 0. And then we're going to go 0, 1, A naught, B. And then we're going to go 1, 1, A, B. And then we're going to go 1, 0, A, B naught. So the code we're using is a gray code. And we don't get to that for another 4 or 5 chapters, but it's a code where only one thing changes at a time. So that 0 changed to a 1, that 0 changed to a 1, that 1 changed to a 0, only one thing changed at a time. And then we're going to do the same thing across the top, B naught, D naught, C naught, D, CD, CD naught. So 0, 0, 0, 1, 1, 1, 1, 0. Now, if I look at this spot right here, and I move from there to there, only one thing changes. So I go from 0, 0, 0, 1 to 0, 0, 0, 0. If I look at this spot here and I go to there, only one thing changes. I went from 1, 1, 1, 1 to 0, 1, 1, 1. See how that works? All right, so on this map, when I change from one place to another, only one thing is going to change, and this map wraps up around itself. So if I go from here to there, only one thing changes. If I go from here to there, only one thing changes. So it's a map that's a circular map wrapping around itself. Yeah, is what we wanted. Now, we're going to go and take the problem on page 204. So we broke the problem on 204, and they said that we're going to come up to, well, I guess no, we're not going to do that one. That's not going to be much fun. See if we can find one that's going to be more fun. Well, we'll just make up a problem. Okay. So we have x is a, b, c, d naught, or a naught, b, c, or b naught, d, or c, d naught. And we're going to want to simplify that for whatever reason. All right. Well, a thing that has 4 letters in it only has one spot on this thing. So there's A, B, C naught. Something that has 3 letters in it will have 2 spots on this thing. A naught, B, C. Okay, something with 2 will have 4 on this thing. B naught is going to be the top guy and the bottom guy. D, B naught, D. C, D naught, I need a different color, is going to have 4 more. C, D naught. Going to have those guys. Now it might be that I can't do anything to make this any simpler. That might be the case. But we'll try. We're very trying. If we group ourselves in 4 this way, and 4 that way, and 4 that's that way, and then we group ourselves in 4 this way and 2 that way. If we were to do that, then we'd have, this guy is B naught, C naught, D, or we're looking at that 4, B naught, D naught. No, not B naught, D naught. A naught, C. So A naught C is this guy. Now I'm going to look at that guy, and I'm going to come up with B naught, B naught, C, and then we're going to look at this guy, CD, CD naught. Okay, well, like for those that are only in their 20s, it's only been 20 years and you haven't seen this. Those in the room that are in their 40s, it's been 40 years, and this is the first time they've seen it. And those in the room that are in their 50s, it's been 50 years. This is the first time they've seen a Karnoff map. So that means we have to do it over and over again, right? Yeah.
It's been
So,
6 years since I've seen it.
Yeah, I mean, this is an amazing thing going on here. So we're going to look at this guy, group of 4 right there. What is true about that group of 4? Well, what's true is that they have to be C, and they have to be A naught. So A naught C characterizes those 4 guys, because D doesn't matter. It can be D or it can be D naught. D doesn't matter, and B doesn't matter. It can be B or it can be B naught. B doesn't matter. The only thing that matters is I have an A naught and a C. Okay, I look at these four guys and it's more obvious because it's sitting on a column that's C, D naught, right? So that's rather obvious. Then I come on these four, coming down this way and coming like that, and I ask myself the same question. What do they have in common? Well, the B naught is in common. A doesn't matter. And the C matters, but the D naught doesn't. So B naught, C. And then there's two left over. I could have done, well, yeah, why don't I do that? I'm going to do something different. I'm going to say I'm not going to do that. I'm going to group these four with those four. All right, well, if I group those four with those four, then that's going to be a B naught D. That B naught D. So now my simplified form is A naught C or B naught C or C D naught or B naught D. And I can actually simplify things further using a Konoff map than I can in Boolean algebra. There's some, and we'll do that on Thursday. We'll go and do a Boolean algebra thing and come up with an answer, and then we'll do a Konoff map and come up with an answer, and we'll find that it's simpler, but there was no way we could get to it using Boolean algebra. We can't get to it from there because our rules don't allow us to get to there from there. So back to our map, A naught B naught AB naught AB naught, and across the top we have C naught D naught, and on the test the map will be there. You just got to use it. CD naught. And I have something when I get done, and I got these guys filled in. And I ask myself, well, what is it? What is it? And I say, well, I can group these guys together, and that would be A naught, C naught, because the B's don't matter and the D's don't matter. And I can group these guys together,
A's and C's.
and there's going to be A, C, and then we're not there yet, but then I'm going to call this A exclusive or B, A exclusive nor C. Yeah, that's what I'm going to do. But we haven't gotten to the exclusive ors or the exclusive nors yet, so that's unfair to show you that. Okay, good enough for today?
Yes. You think? Something that's it up for the rest of the year.
Yeah. So start teaching this to your children in about 3rd grade.
There's not going to be a quiz on this, is there?
No, only a test.
When she doesn't eat her dinner, the teacher.
Yeah, that's right. When she doesn't want to eat her dinner, teach her this. Yeah.